Today we're covering Chapter 19, Thermal Properties. Let's start off with the objectives. After completing this chapter, you should be able to describe how atomic vibrations relate to temperature and influence thermal behavior, explain heat capacity and apply the relationship Q equals C delta T, calculate linear and volumetric thermal expansion using the linear expansion coefficient and volumetric expansion coefficient, explain thermal conductivity and apply Fourier's law to determine heat flow, and finally, calculate thermal stresses in constrained materials using the thermal stress is equal to the modulus of elasticity times the linear expansion coefficient times delta T. Moving on to the introduction, thermal properties describe how materials respond when heat is applied or when their temperature changes. These responses depend on atomic vibrations, bond strength, and material structures such as crystal structure, defects, and phase. Why these properties matter? These matter because of real-world issues such as thermal shock in ceramics, dimensional changes in bridges and engines, electronics overheating, and temperature limits in packaging. Check your understanding. Why does a ceramic coffee mug crack when cold water is poured into a hot mug? Because it has low thermal conductivity and low thermal toughness. Now moving on to atomic vibrations and thermal energy. As temperature increases, atoms vibrate with increasing amplitude and increasing energy. The textbook figure shows the potential energy well, where the vibrational amplitude increases as temperature rises. Because the curve is asymmetric, this leads to thermal expansion. Atomic vibration is the root cause of heat capacity, thermal conductivity, and thermal expansion. Heat capacity. Heat capacity is the amount of heat energy required to raise the temperature of a material by 1 degree or a given amount, but note that 1 degree is standard. There are two types. Specific heat capacity at constant pressure, CP, which includes expansion work, as well as specific heat capacity at constant volume, CV, which doesn't have expansion work. So CP is always greater than CV. The equation Q equals C delta T, where Q is known as the heat energy absorbed, most of the time measured in joules. The unit is joules. C is the heat capacity, and delta T is the change in temperature. Temperature dependence. Heat capacity increases with temperature because atomic vibrations increase. From the graph I pulled out of the textbook, metals rapid rise, then flatten out. Ceramics gradually increase. Polymers are sharp change at glass transition temperature, which is known as TG. I put in a glass transition reminder that polymers become rubbery above TG and brittle below TG. Here's a mini example. A 250 gram aluminum block with a heat capacity of 0.897 joules per gram degree Celsius is heated from 25 degrees to 75 degrees. How much heat energy is absorbed? The mass is 250. We can write down all of our givens. We know the heat capacity. We can find delta T because we know the final and initial temperature. Finally, we can solve for Q since we have everything for that formula, and you'll find 11.21 kilojoules. Linear thermal expansion. Most materials expand when heated because atoms vibrate with greater amplitude and need more space. The equation is delta L equals the coefficient of linear expansion times L naught times delta T. Each variable means something different, so alpha is the coefficient of linear expansion, L naught is the original length, delta T is the temperature change, and delta L is the change in length. Here we have the heat capacity for a bunch of different metals, as well as the coefficient of linear expansion. That's from the textbook as well. Here we're going to rank some materials from highest to lowest linear expansion coefficient. The highest being polymers, the second being composites or nonmetals, the third being metals, fourth ceramics, and fifth diamond, which is the lowest. So why do polymers expand most? Well, they have weaker secondary bonds. Thermal expansion consequences, some real-world engineering problems. Concrete sidewalks need expansion joints. Railways buckle if they're overheated. Engine pistons require clearance or they seize. And composite materials must match the linear expansion coefficient to prevent demonation. Volumetric expansion, used when entire volume changes. So we have delta V equals beta V naught delta T, where beta is equal to 3 times the linear expansion coefficient, and beta is otherwise known as the volumetric thermal expansion coefficient. Now we have thermal conductivity, and this is where Fourier's law comes in. So thermal conductivity describes how easily heat flows through a material. The equation is here, Q equals minus K over dt over dx, where Q is the heat flux, which is measured in heat per unit area per second. K is the thermal conductivity, and dt over dx is the temperature gradient. Why metals conduct heat well? Metals have free electrons that transfer energy. They also have a crystal structure that is uniform to vibration transfer. Metals have high K, ceramics have low K because atoms are tightly bonded. Polymers have very low K because they are disordered and have weak van der Waals bonds. Thermal stresses. Thermal stress occurs when a material is prevented from expanding. This is the equation. The thermal stress is equal to the modulus of elasticity times the linear expansion coefficient times delta T. Here's what each variable is. So the thermal stress, the modulus of elasticity, coefficient of linear expansion, and temperature change. Thermal shock resistance is highest in materials with low modulus of elasticity but high thermal conductivity. So ceramics fail because they have high modulus of elasticity and low thermal conductivity. Here's a full example. So a steel rod with an initial length of 1.2 meters at 20 degrees is heated to 120 degrees. The coefficient of linear expansion is 12 times 10 to the minus 6 per degree Celsius, and the Young's modulus of steel is 210 GPa. So, calculate the change in length. We saw that formula early on. We can write down everything we're given that we'll need for this. We'll need the initial length, 1.2. We will need the coefficient of linear expansion, 12 times 10 to the minus 6. And we will also need delta T, which is 120 minus 20, giving us 100. You can plug that into our formula, and you will get 1.44 times 10 to the minus 3 meters. And in part B, it says if both ends are fixed, calculate the thermal stress. For the thermal stress, we need to use the modulus of elasticity, so 210 gigapascals, but we want it in pascals, so you need to know the conversions for that. So if you do times 10 to the 9, you'll get it in pascals. And then we also already know the other variables for the equation. So you can plug that in, and you will get 2.52 times 10 to the 8 pascals. So now we can do a quick little concept check. Which material has the highest thermal conductivity? The answer is diamond. Why do polymers expand more than metals? Because they have weaker secondary bonds. Which thermal property tells you how easily a cooking pot heats up? That's the thermal conductivity. And why does glass shatter under sudden temperature change? Because of low thermal shock resistance. And after that, I just have a citation from the textbook. That brings us to the end of the notes, and this chapter ties together heat capacity, thermal expansion, conductivity, and thermal stress, all rooted in how atoms vibrate and how materials structurally respond to temperature. Thank you.